unit-static mean field equation, and now like with this idea that we are looking for some second-order phase transition, meaning that we can consider the limit of m being small, finite but small. So if m is finite but small, let's see what is the criterion for having a solution, a non-trivial solution to this equation. So this limit, you can just well, simplify this expression. So the Fermi distribution function at minus epsilon about plus epsilon in the limit of m bar going to 0. This is just giving a minus 2 times m bar, the derivative of the Fermi distribution function. Now in the limit t going to 0, the Fermi distribution function is a step function from 1 to 0. So this will give us a minus the delta function. Okay, so the minus compensates. So the limit m going to 0, t going to 0, this gives us 2m bar delta epsilon, which pins epsilon to the Fermi surface, epsilon minus 3. Okay, so in the limit for m going to 0 plus, so second order phase transition, and t going to 0, so let's look for a quantum critical phase transition. Then we get here 2 times m bar the delta function, the 2 cancels this. This is the interaction strength, and then the derivative, the delta function just pins the density of states to the Fermi level. Okay? So in this limit we get here an m bar equals to u times u0. Okay? So just using that minus m bar epsilon plus m bar becomes minus 2m bar delta epsilon at Fermi epsilon, which is plus 2m bar delta epsilon minus 3. Okay, so using this, we find the condition for having a second order phase transition. So this will denote the critical value, sorry, the m bar cancels, so it's 1. This will be the critical value at which the second order phase transition takes place. So this would be at 0 temperature, so this will be the quantum critical point. Okay? So this is called the Stoner criterion. For the quantum phase transition. So the phase transition that takes place at 0 temperature. Okay? And actually what we recognize, well, that's exactly like the condition that we found from the transverse susceptibility. So that's exactly the point where the susceptibility just blew up. Okay? So summarizing, from the mean field equation we find a non-trivial solution when temperature goes to 0. So at 0 temperature we find a non-trivial solution once the critical interaction strength becomes larger than 1 over 0. Okay, so this denotes the phase transition point. Okay? So u equals to this critical value defined by the Stoner criterion, is the critical value beyond which, and we will later see like what this beyond which means. So far we are really concentrating on the phase transition point by considering this limit. Okay? Beyond which the paramagnetic ground state of the non-intaking electron gas becomes unstable to magnetic order, and actually so finite expectation value for sigma z builds up, so we get ferromagnetic order to transition which takes place at 0 temperature, so it's a quantum phase transition. Which is driven by quantum, not the usual thermal fluctuation or pure temperature. And this is now here just a statement which doesn't tell you too much, but this is something we will look into. So just what we will do after the mean field analysis, we will derive an effective theory for fluctuations at the quantum critical point, okay? So actually, the mean field program is only the first step. Like the second step should be derive an effective theory at the quantum critical point and look at its renormalization. So this is what we're not going to do like now, but maybe later. So one can look at the RG properties to see if actually the mean field solution that one has is stable. Could also be that it's just destabilized by quantum fluctuation or thermal fluctuations, which will then destroy the order that you find here. So the order which would correspond to finite expectation value. So this should be analyzed by some RG analysis based on the theory of fluctuations. And there then it's important that if we derive the effective theory, what we are going to do, this will be an effective theory that is still where the degree of freedom, like the fluctuations, still depend on, let's call the fluctuations by delta m, they still depend on the imaginary time. So there can be fluctuations in imaginary time, which is dynamics, and therefore it's like quantum fluctuations. Now if you would go to the high temperature limit, so the integral here is from 0 to beta, so from 0 to 1 over t. So at high temperatures, this would be like a small interval of imaginary time. You can imagine like a particle in a box, where you have like an infinite box. It's simple to have fluctuations, spatial fluctuations, but once the box becomes smaller, you pay a price for having fluctuations, which scale is 1 over the distance, so here with temperature. And once temperature become very high, you can imagine, well, the spatial or the temporal fluctuations will just be too costly, so you will only have the constant solution, which will then make the fluctuations be independent of tau anymore. Okay, so this will be just a constant. So at high temperatures, one can see, like, just trying to give you an idea that quantum fluctuations are not relevant anymore, and you can just study then the renormalization properties due to thermal fluctuations. So the fluctuations are different at, let's say, 0 temperature, where you have to take into account the full dynamics of the imaginary time, and at finite temperature, where in a way the fluctuations in imaginary time just are not relevant anymore. Okay? So this is why here we talk about quantum phase transition driven by quantum fluctuations, because the effective theory at 0 temperature always will have to take into account the fluctuations in imaginary time. Just brief outlook. Okay, so this is at 0 temperature. Now one can also look at this equation at finite temperatures. So at finite temperature for some given value of u, then you will find, again going through the same manipulations from the mean field equation, you can still in the limit m going to 0 plus, use that the Fermi distribution becomes a derivative, but now in the 0 temperature limit it's a delta function. This is just some finite function. Okay, so if you look at finite temperature, the criterion becomes here still containing the derivative of the Fermi distribution function. And this here is what you can call spin susceptibility at finite temperature T. And if this is then 1, you have for a fixed value u, figured out if you solve this equation, the critical temperature at which the transition takes place in this species. Okay, so that's looking not at the quantum phase transition, but at the phase transition at finite temperature. And so this is the Stoner criterion of finite temperature. So this was the Stoner criterion for the quantum critical point at t equals 0. This is the Stoner criterion of finite temperature. Now, what you can do is you can now study this equation here for a given model. Okay, we found that this result actually was independent on the dispersion and on the dimension because it simplified just to the, well, I mean the density of states of course knows about like the dispersion and the dimension, but we could simplify this to just the density of states at the Fermi surface. So one could here, for example, study this equation if you like, find the phase boundary at finite temperature for a 3D system. Like continuum model where the dispersion is just the usual quadratic dispersion. And for which the density of states goes with the square root of the energy. Okay. So the density of states was 3D system with quadratic dispersion was the square root with the energy, so we can write it as the density of states at the Fermi level when this is just 1, and then at finite energy it's multiplied with a factor epsilon over epsilon Fermi square root. Okay, for this model you can just insert then, well, the density of states and calculate here what the derivative of the Fermi distribution is, and you find the following equation for the Stoner criterion. So 1 equals, well, given u and the critical temperature at which the transition takes place, you would have to solve this equation so consistently square root of x cosine hyperbolicus, which is the derivative of the Fermi distribution function. You just changed from epsilon to dimensionless units, which is, I guess, x over tc. Now there's one little complication here, which is if you're at finite temperatures, the Fermi energy and the chemical potential differ from each other, and also they're related. Like if you have a finite density, you can calculate how the chemical potential changes as a function of temperature. So in this equation, you should still include this finite temperature correction, but then you can figure out from this the phase boundary. So this is x minus then the chemical potential mu over 2Tc, and Tc would be the critical temperature. Okay? At which transition takes place. So with these equations, then you arrive at the following phase diagram based on the mean field analysis. That you have tuning parameter for the phase transition, which is the interaction times the density of states. So that we already commented on, no? And like that's what we already saw from the diagrammatic perturbations here, that the combination that matters is not only the interaction, but it's the interaction multiplied with the density of states, meaning that even if you have a small interaction, if it can be compensated for by a large density of states. Okay? So at the value 1, we have the quantum critical point. And then if you look at this equation, you see, well, at finite temperature, this will shift the boundary for the transition to higher values, because quantum fluctuation for thermal fluctuation want to destroy the order. So here we have now temperature. At 0 temperature we have the quantum critical point. So here we would have ferromagnetic order above the critical value, and here we have just a paramagnet, PM1 paramagnet, and here is the quantum critical point, and here's the phase boundary at finite temperature. Okay. So this is the mean field diagram. And what of course one should do is one should not rely on this, but later on look at, ask if this is stable against fluctuations, any kind of fluctuations which can be thermal or quantum. So this one has to do by an RG analysis. Okay. Questions up to here, or now?
Just, o que é o X ali?
SX, o que você fez, você escreveu essa equação usando dimensional quantity. Então, o que você vai fazer aqui é simplesmente introduzir X como epsilon dividido por TC, que é o critical temperature. Por isso está aparecendo TC aqui, o square of TC, porque isso é funcional. Então, isso seria, para fazer isso da forma mais simples, então tem a dependência de TC sobre epsilon Fermi aqui, e aqui tem essa complicação μ sobre TC, tá? Isso eu simplesmente divido. Ó, aqui tem, isso é a derivada da Fermi distribution, do cosine, e agora, para analisar isso de forma certa, tem que olhar que μ, dependendo da dimensão, é epsilon Fermi mais tem p squared sobre blá blá 12 t squared, blá blá blá, tem correct que tem que botar aqui também. Não lembro exatamente, mas depois achar a solução dessa equação e isso vai te dar a phase boundary aqui. Okay, but conceptually what you now want to do, so this is the mean field analysis. We found now one example of a problem where there are solutions to the mean field equation which are non-trivial and which actually build up once it actually becomes larger than some critical value. And this was already reflected in our analysis of the transverse susceptibility. So we saw that at some point it doesn't make sense anymore to build on the non-interacting reference state or non-interacting ground state as a reference state around which perturbation theory can develop. And now we understand, well, it's simply based on the observation that of some critical value there is a ferromagnetic phase building up, and this is then the right ground state around which one should evolve the theory. And this can now be done systematically in terms of the field integral by now expanding the action around the non-trivial mean field. Then we can derive the effective action for fluctuations, and this is what we are still going to do. So let's see if we start, but the idea is derive the effective theory for fluctuations, and then the next conceptual step would be to look at it at its renormalization properties, and there again it's the difference if you look at the quantum critical point or look at here. So here it's dominated by quantum fluctuations, and up here that will be, the effective theory will be dominated by thermal fluctuations. So that's then the final step, derive the effective theory of fluctuations around wherever you want, but what we will do is we will derive the effective theory around the quantum critical point. Alguém de vocês trabalha com bosonization? Eu sou o Eric. Eu sei que o Eric está fazendo alguma coisa com bosonização. Vocês também ou não? Estou pensando o que eu vou fazer ainda na quarta-feira. Bom, vamos ver. Sim.
Você fazer essa análise de dados, você teria que considerar o density channel e botar outro campo.
Outro campo. Então, agora seria, se você está realmente falando, a gente só concentrou em um canal, o certo seria, vamos incluir outro Rabat-Satonovich que vai tomar em conta as fluctuations da densidade e olhar o que é que vai aparecer. Eles são decoplados.
Você pode homogenear.
Se você...
Um vai acoplar com o outro.
Na teoria efetiva, um vai acoplar o outro.
Mas só quando você faz
quando você vai derivar a teoria efetiva. Mas, nesse caso, por exemplo, é bem interessante, uma vez que a gente olha, a gente não falou nada sobre desordem, mas sistemas desordenados também é interessante porque se você pegar um sistema mais simples, simplesmente eletrões movimento num ambiente desordenado, sem interações e nada, ainda existe o que a gente está fazendo aqui, só para falar muito geral. O que a gente considerou é um exemplo que você vai ter um finite expectation value, o mean field equation que não é trivial. Esse mean field solution que não é trivial quebra uma simetria. No nosso caso, a gente singled out z direction do spin. Então, isso quebra agora z direction. A gente poderia ter feito mais geral, um comentário que eu fiz, que você sempre pode decoplar o local interaction em termos de density e do spin. E a gente poderia feito toda a análise como a gente fez agora, em vez do campo M, pegado um campo S como vetor. Tá? A análise teria sido totalmente igual e a gente teria achado que a finite expectation value agora vai apontar em alguma direção. Por nossa escolha, a gente já singled out z direction, por isso o finite expectation value quebra z direction. Nesse caso, você iria quebrar uma O3 invariance, porque a magnetização aponta em uma direção. Agora, existe um teorema que te fala que se você tem uma simetria contínua, que você quebra, você vai gerar soft modes, Goldstone modes. E esses são os modos que nossa teoria vai depender. Esses são os modos interessantes, que aqui são os Goldstone modes do magneto, que simplesmente, se você tem todos os pins apontando uma direção, se você faz uma modificação de todos os pins ao mesmo tempo, isso não vai custar nada. E aí você vê que se você faz pequenas variações homogênicas no limite Q para zero, wavelengths para infinito, isso vai custar nada, então vai ter uma ação que depende, por exemplo, de Q e pelas simetrias deveria depender de Q quadrado. Então são Goldstone modes com a ação que está desaparecendo. Existe uma quebra de simetria, existe Goldstone mode. Agora vamos voltar para o sistema desordenado de eletrões. Você pode, de novo, fazer uma teoria efetiva depois de integrar a desordem e fazer uma mean field analysis. Nessa mean field analysis também você vai quebrar uma simetria contínua, que é um pouco mais complicada porque tem a ver com o grau de liberdade interna. Mas o que eu quero dizer é sistema desordenado, eletrões simplesmente movimentando num ambiente desordenado, tem uma teoria efetiva descrita por Goldstone modes, soft modes. Tá? Agora, você pode perguntar, o que acontece nesse Stoner transition, num sistema desordenado? E aí você tem que fazer isso, você tem que pegar em conta os soft modes, que são por causa da desordem, e ver como eles se acoplam nesse grau de liberdade de espírito. E existe, assim, ainda está discutindo, assim, mas tem um trabalho bem interessante que já tem uns 10 anos, mas ainda não está sendo clarificado se realmente é assim, mas existe um trabalho que diz que sempre o que vai acontecer é quando você tem desordem, a transição de fase segunda ordem, que a gente viu aqui, vai virar uma transição de fase primeira ordem pelo acoplamento dos spin fluctuations ao Goldstone laws que estão lá no sistema desordenado. Então, é um processo assim, pode fazer essa análise e falar, ó, sistema desordenado, vamos só mais concentrar no spin que a gente está interessado, mas é complicado, pode ser que você está não vendo uma coisa. No caso de desordem, é mostrado que tem que tomar em conta as flutuações suaves, soft fluctuations, por causa da desordem. Agora,
Mas quando você faz essa conta, a tendência do channel e o channel, você dois campos, eles só vão, quando você bota
na mean field equation, eles estão acoplando
mas o shift você não considera uma coisa do outro?
Sim, mas vai aparecer sempre, olha, se vai ter dois campos, vamos chamar de campo 1 quadrado S2 φ e igual a 1 a ter quantos componentes você quer. Mas se vai ter no trace lock, vai sempre ter o G-, tá? Os livres, aí você vai ter o acoplamento φ1, φ2 e tudo. Aí se você vê quando você faz a mean field equation, você vai ter a variação daqui, vai ter um φ1, φ2, blá blá blá, igual a alguma coisa, e aqui vai ter 1 sobre esse denominador. E aí eles estão falando um com o outro pela mean field equation. E foi isso que eles observaram quando você tem um sistema desordenado, o mean field equation não vai ter mais uma solução, no caso do Stoner com desordem, não vai ter mais uma solução contínua, mas você vai para ela pode mudar um signo em um fator e fazer que você vai ter uma transição de primeira ordem. Então, vai aparecer primeiro na mean field equation, depois quando você considera os fluctuations, eles vão acoplar um ao outro. Tá?
Outra vez.
Certo?
Mas vai ficar bem mais difícil de você tratar esse problema, né?
É,
Porque você vai acoplar os parâmetros de ordem.
Muito mais difícil. E isso você já vê que Stoner é uma coisa que a gente pode fazer em uma hora de aula, 2 horas. Mas o problema Stoner com desordem foi proposto 10 anos atrás, que vai virar uma transição de primeira ordem, mas ainda não está sendo esclarecido. 10 anos atrás. Então é bem mais complicado, sim. Agora você pode fazer a mesma coisa, assim, você acopla no density e no spin nesse caso e vê o que acontece. Só que no nosso caso a gente já viu que o density tem uma solução trivial. Então, pegando a solução trivial no mean field, você fica com a mesma coisa que a gente já teve. Depois pode ver aqui que as flutuações modificam, mas no mean field já não tem essa influência. Mas com desordem vai virar uma coisa bem interessante.
Você considera esse mean field quando você vai fazer RD, análise, esse
vai renormalizar.
Mesmo que seja do
Certo. Verdade. Tá. Mais perguntas? Tá, então vamos lá. O segundo passo, step 5. Vamos só começar, a gente não vai... Effective theory. For fluctuations. And what we will do here is concentrate on the theory at the quantum critical point. So here, near the quantum critical point. So that's what we're interested in, because this is quite an interesting action, effective action, that later on, I mean, if we continue, we'll consider this as an example for quantum critical fluctuation. So the idea of this system here. So what you do is start out from the action that we had in terms of the magnetization, which I write down here again for, I think it's for calculations most convenient in momentum space. And then we have the 3 property. So what you do is just you write as M Q as the mean field solution plus fluctuations. And this you insert into the action. And what you will get is an action which depends on the mean field, and then you will have the fluctuation part, where again you make the expansion around the mean field, so this will only appear in quadratic order fluctuations. Okay, that's what we already discussed several times. So what you will have to do, well, you plug in this parameterization here, so you get the mean field contribution, then the linear term disappears because you know it's mean field, and there will be a quadratic term, and you also plug in this ansatz here, and then you have a trace log, and what you do here is an expansion in the fluctuations. In the same way that we did the expansion fluctuations for the weakly interacting electron gas. Okay? So what you use then, you can always write the trace log. Well, if you plug in the parameterization, you have trace log G0 to the minus M minus sigma Z mean field minus sigma Z Lm. So you can call this here the Green's function to the minus 1 in presence of the homogeneous field M. Okay, so this just has a simple, how do you call it? There's a name for it, I now forgot, like spin coupling to the external field, sigma Z times M. It's Pauli. It's a simple Pauli term. I think it's Pauli term. It's Pauli, no? Yeah. Just a simple like coupling to a homogeneous static component. And then you have here the fluctuations. So this you can then write as a trace log times M. Okay. I just do it once. I mean, we already did it once explicit, just an usual thing. So you can write trace log in this way. Now you can factor out the Green's function for the mean field solution, and then have here the trace log of 1 minus Gn sigma Z delta M, which you now expand, assuming that the fluctuations are small, reduce the expansion of the trace log. No? And here we again use to the trace the log just obeys the usual rule, so we can just expand this as trace log. So copy this first line, and then can expand to the trace log as 1 over k, trace G and sigma C delta M to the power of k. Okay? So if we expand this in powers of k, well, the first order contribution will combine with the linear term from M bar and delta M from this here to cancel. This is just because we have the mean field. So this expansion here starts around the second order, and then we can just use the symmetry. If you have the integral over delta M, you will see that well, you have the symmetry delta M to minus delta M, which will cancel out always all odd terms. So if we make the expansion, this will correspond, this will start with k equals 2, and then the next order will be k equals 4, and so on. Okay? So for our analysis, what we will do first is go to take into account both terms, the k equals 2 and the k equals 4. Okay? So for our purposes, for the effective theory, we should take into account the fourth term, and why we should do this becomes obvious once we have derived the theory, but it's necessary for the stability of the theory. Then we can see like how good was our assumption about second order phase transition, and actually we will see that there can be also a first order phase transition. Now if you really want to take into account the theory of the first order phase transition, you should then expand this to sixth order, but this is what we're not going to do. We just consider fourth order. Okay, so this is using the symmetry. And then what we can simplify is, well, if we are interested in the theory at the quantum critical point, the m is just 0. No? So it's, if we have the second order phase transition, quantum critical point, we can substitute this by 0. So we have to calculate this and this. And this is what we are going to do on Wednesday. Okay, this is like taking. So maybe we'll do this a little bit more in detail, because it's good to do this once in detail. But again, you have a systematic way to look at the fluctuations, and there we can then look at the phase diagram and see if there's something like a second, first order phase transition also. And then I have to see, so probably this will take, I don't know, half an hour, 40 minutes, so maybe I'll make some more. So I don't know what to do then. It will take half an hour, so I could try to so